idea is, so our question is how to calculate chemical shift. So this is the problem that we are currently facing. How do we calculate the chemical shift? And we know the chemical shift is going to be in hertz. Right? Chemical shift is a frequency. Okay. Therefore, we're going to be using hertz. So, for example, we have 1 Tesla. So this is going to be 147 hertz. We have 1.5 Tesla. So this is going to be 220 hertz. And then we have 3 Tesla, which is going to be our 440 hertz. Okay. So these are approximate. If you do it, you'll find out some rounding stuff is going on here. But these are pretty good starting point numbers for our chemical shift. And so we need to talk about how these frequencies, how the shift in frequencies is affecting our image. So we know that chemical shift is going to happen in the frequency direction of our image. And one of the things then we need to ask ourselves is, how do we determine our frequency axis in our image? What is used to basically create this frequency axis in our image? And the answer there is going to be our receive bandwidth. So our receive bandwidth is going to, play into calculating our chemical shift. So one of the key things we need to know, one of the key variables we need to know is, what is the receive bandwidth?
Just for a refresher,
yes.
What is receive bandwidth one more time?
Great question. So receive bandwidth is the range of frequencies we are using to create our image. So basically, along our frequency axis, along our long axis usually, we have all of this anatomy. We need to give this anatomy its own unique frequency. So down here, the anatomy is going to have a low frequency. Up here, the anatomy is going to have a high frequency. So how many different frequencies are we going to have within this region? That is what the receive bandwidth will tell us. So if the receive bandwidth, in this case, is 48,000 kilohertz, this anatomy here will be covered by 48,000 frequencies. We're using 48,000 frequencies to give each piece of anatomy its own unique frequency. So we can cover 48,000 values. So we have all this anatomy, all of the anatomy has its own frequency. But we're not going to pick these frequencies one by one because they're too small. The amount of volume they cover is too small. What we're going to be looking at is pixels and voxels. So the next thing we need to know is going to be about our pixels or voxels. How many pixels or voxels in the frequency direction? Okay. How many pixels and voxels do we have in that frequency direction? In our case, because our matrix size is 128 by 128, we know that we've got 128 pixels in that direction. So basically, we have our matrix, okay? So we have our phases, frequencies, and we have got all these pixels. Okay? And so we've got, in this case, we have 128 pixels here, in our frequency direction. These 128 pixels are being represented by our receive bandwidth. So in this case, it is our 48,000 hertz, right? Our 48 kilohertz. So all these pixels represented by this many frequencies. So now we can talk about how many frequencies are being covered per pixel. So I've got 128 pixels, 48,000 frequencies. Frequencies per pixel, we're just going to divide. So we're going to do our 48,000 divided by the number of pixels, hertz per pixel. And so this gives us 375 per pixel. So now we can say, okay, inside each pixel, we're covering 375. Here's the lowest 375, next highest, all the way up into the highest 375 frequencies, and that uses up all 48,000 frequencies in our frequency direction. Okay. So now we know that each pixel basically covers a span of 375 hertz. So from, let's use an easy number, 0. So from 0 frequency all the way up to 375, that is 1 pixel. From 376 all the way up to 750, that is our next pixel, right? So on and so forth. So each pixel contains this many frequencies. And then we come back here to our chemical shift. So we're like, okay, each pixel has this many frequencies. My chemical shift covers this many frequencies, right? I'm moving water and fat apart this much. Right? So water's over here, fat's down here, right? High frequency, low frequency. And so then it's like, okay, well, these two are 440 hertz apart. How many pixels is that going to be? Well, okay, I start with my 0, so 0 to 375 is 1 pixel. Okay, still have a little bit left over. So from 375 to my 440, that covers about another half pixel. Right? So if you look at our chemical shift, then it's like, okay, it's a little bit more than 1 pixel. That is how much we will see these apart by in our final image. Okay? And so basically the way to do that is just the received bandwidth divided by matrix, find how many frequencies per pixel. From there, figure out what your chemical shift is, and then take your chemical shift, divide by frequencies per pixel. That gives you the total size of your chemical shift. And then if you want, you can take this one step further and say, well, these pixels also represent a field of view. So now, if my field of view is this big, I can talk about, okay, I need this many frequencies to cover my field of view. I need this many pixels to cover my field of view. Right? And so now we can throw field of view into this equation as well. So once we know how many pixels of chemical shift we have, we can look at field of view. Okay, field of view is, let's say, 10 centimeters. I need 128 pixels to cover 10 centimeters. So how much distance is covered per pixel? Right? Same idea as our frequencies. Calculate how much distance per pixel. I know how many pixels my chemical shift is, so now I can measure my actual distance as well. Does that make sense?
Yes.
Okay. And then you said you had